NanoHub U, online instruction.
Hey everyone, welcome to lecture 418. So continuing on the theme of thermal transport, but now connecting more closely with optics, we're going to talk about the topic of blackbody radiation, which we had touched on briefly before, but we're going to try to explain in more detail. Okay, so first of all, just the question is, where is this all coming from, this blackbody radiation? And so probably the way to think about it, coming from a photonics perspective, is the number of states first that are present in a photonic band. Okay, so if we have a black body, then we can actually determine that for a homogeneous medium of index 1, that we have a density of states of the photon modes that's calculated by this. And remember, density of states is just defined as delta of omega minus omega nk, where omega nk are the bands of the mode, and then summed over all n and k values. And so we can easily show that if we just have a homogeneous medium and the bands all go like ck, then we would get this solution. And so I just have to skip this for the sake of time, the derivation. But then we can show also that in addition to this photon density of states, the occupation probability is a very key consideration. And so for a photon or a boson in general, then the probability of occupation is given by the Bose-Einstein distribution. Bose-Einstein distribution is usually written as 1 over e to the h nu over kt minus 1. And so this is related to the Boltzmann factor. So if you consider the Boltzmann factor, it's usually given as e to the minus delta E over kt. Of course, the delta E, or energy difference in the case of photon absorption or emission, is h nu, energy of the photon itself. And then you have the minus sign because it's in denominator, right? But this extra minus 1 is very important, and this becomes important especially if h nu over kt is not very large, right? Because then if you were to expand this term, then it become 1 plus h nu over kt minus 1. And so that's going to substantially deviate from the e to the minus h nu over kt for small h nu over kt. However, for large values, of course, the Boltzmann factor is a very good approximation. But then if we put these things together, the density of states times probability of occupation of the states, then that's actually going to tell us what we call the density of occupied photon states. N of nu over the volume, B times d nu. And so then this gives us this overall expression, 8 pi over c cubed times nu squared times this occupation factor, 1 over e to the h nu over kt minus 1 u nu. So that's a very important start for our problem. And now the next thing we have to do is actually combine that with the average energy of the mode. Okay, so we multiply by an extra factor of h nu. And of course, we've already accounted for this occupation factor, so we don't have to include it again. And so now if we combine it with what we had previously, h nu times that, then we get this h pi 8 times pi h nu cubed divided by c cubed times this occupation factor. And then this actually directly tells us something about the radiation spectrum of the black body. And so what you can see in particular is very interesting, which is that as a function of frequency, that the peak emission is actually going up linearly with temperature. And so at low temperatures, let's say at the cosmic background radiation temperature, which is around 3 Kelvin, then of course the emission is in relatively low frequencies, maybe on the order of a terahertz, okay, or even in radio frequency range. And then you get up into about 10 terahertz at liquid nitrogen temperature, which is 77 Kelvin. Go up to room temperature, the peak is actually at 10 microns. This is the wavelength here, or you could also write it as about 4 or 3 times 10 to the 13th or 30 terahertz. And then if you actually heat something up much higher to 1000 Kelvin, you can actually see that the peak has now shifted to about 3 microns. And then at 6000, which is about the temperature of the surface of the sun, then you can see that the peak is invisible, which of course is why we probably see visible light. And so this is very important because it's allowed us to connect both blackbody radiation at room temperature, what we see from the sun, as well as cosmic background radiation, all in a single framework. And so, of course, the key motivation behind this is essentially the Bose-Einstein distribution. And so it's ultimately driven by quantum mechanics. And just to write down explicitly like what is happening as a function of temperature, we can actually refer to this as Wien's law. And so this is the exact expression, which is that the maximum wavelength as a function of temperature is going to be 2898 divided by temperature T in Kelvin. And so this actually reproduces all those results I was talking about earlier, like 10 microns at 300 Kelvin and so on. And so this is just showing like what happens for 3 different temperatures of 3000 to 6000. It actually shows like why, if you think about it from optics perspective, why would a slightly cooler star look red, like a red dwarf? Why would it look red? But then why does the sun look white to us? And then, of course, a star even hotter than the sun, like Rigel, would actually look blue because it would be even further blue shifted into shorter wavelengths than what we see as white. Now, of course, there are a lot of applications for this sort of technology once we understand what's going on here. And so one example is thermography. And so this is essentially imaging any sort of object that's emitting thermal radiation. And so, of course, we can image the sun very easily because we see invisible and we have visible detectors, but we may also need special equipment in order to actually be able to visualize the sun and to see sunspots and other features that our naked eye just doesn't permit us to directly look at. But then at like obviously like more terrestrial scale, then we can also look at human body heat in the mid-infrared. And so this has actually become a big deal in the last few years because if people are trying to screen for sick passengers, then it becomes very possible to actually do mass screening. So basically, as people walk by, to see if they have elevated temperatures and then to talk to them if they are very sick and have an elevated temperature. This is just a thermal image of a dog. And it's just showing like that the dog's head is usually a little warmer than the rest of the body. So I guess he's thinking hard. And this is actually image of the galaxy and showing that in addition to the cosmic background radiation, you can have like regions that are actually much hotter as well. And so you can kind of do astronomy studies using this thermal imaging. In the next lecture, we'll talk about some other possible applications of thermal radiation.